Next, let's talk about the geometric series on page 456. Now, the geometric series was the geometric sequence was mentioned in the previous section, something that looks like this: r to the power, say, n. Okay, as n goes to infinity, this particular sequence will converge if r is less than 1. Now, at the time, I didn't say that much about it. I just said that if you multiply by a number that's less than 1, you are cutting yourself out, right? You're getting less and less, so you eventually go to 0. That's basically what the book said too. However, the more I thought about it, it's like that is actually not enough proof, because it might be going less and less, but how do you know it goes to 0? Maybe it goes to 1/2 or 1/3 or 0.1 or some other number. Just because it's reducing doesn't necessarily mean it's going to go to 0. How do we know that it actually goes to 0? So I went ahead and proved it. And the way we prove it is based on the theorem that if r to the x, if the function r to the x goes to 0 as x goes to infinity, then r to the n, the sequence also goes to 0, because we have a theorem that says so. So we have the proof that this particular function, r being some number that's less than 1, as x goes to infinity, this has to go to 0. Okay, and this go to 0. Well, does it? That's our question. To prove this thing, what we're gonna do is and now that I have to prove that, then we're gonna use the standard trick of the natural log. So we let y equal to r to the power x, then natural log of y equals to x natural log of r, and then where r is less than 1, which means this thing is negative, right? The natural log of numbers that's less than 1 is negative. So as x goes to infinity, then this is negative, x going to infinity. So natural log of y will go to minus infinity. And if that is the case, that means y itself is going to 0. And in other words, r of x does go to 0 as x goes to infinity. So that is the official proof, I guess you can say it, which the book skipped, and I sort of didn't think about it in the last section, but I should have mentioned that. But the point is, it does work that r to the power n does go to 0 as n go to infinity if r is less than 1. That's very important. If r is equal to 1, of course, you just have a bunch of 1s added up forever in the sequence, then go to 1, but the series then go to infinity because you have a bunch of 1s added up. And in this case, it would be a bunch of 8s because r is just 1. And if r is bigger than 1, then it goes diverges as well, because, well, it just does, right? I mean, because you have a bunch of 8s that's getting bigger and bigger. So it will go, well, bigger and bigger. In fact, it either diverges straightly or bounce back and forth, and bouncing harder and harder and stuff. So then that's the geometric series. Now the geometric series, if it converges, have a fixed formula as to how that converges. Right? And the formula is, look at the next page. It's a very simple formula. Okay, the geometric series converges in the next page. And the series that I seen in the book here, this one, okay, which is written down here in this blue part. Okay, and then as you can see, it converges to a fixed number, that's a over 1 minus r. Now the proof of that is very straightforward, so please do that proof yourself as part of your homework. And after you prove the solution to the geometric series, please do as your homework example 5.9 about doing the geometric series. You just plug it into that simple formula. Geometric series is a over 1 minus r, right? Yes. And then the next 5.10, the same thing. And they have you do geometric series for it, I guess. Well, whatever. Okay, there's actually an easier way than geometric series to calculate repeating decimals that was taught in algebra or something. But I guess it doesn't hurt to use geometric series on it either, because that's not much harder, right? Geometric series has a very simple answer. And then example 5.11 is mildly interesting to look at the Koch snowflake for the first time. Yeah, so go ahead and look at that. Again, that's just geometric series. And then next we'll look at something. I'm on page 462, where we look at something called telescoping series, which we have mentioned earlier. A telescoping series is a series that, here's the one we mentioned earlier, and that the book sort of didn't want to mention. The book just said that it looks that way. Well, it doesn't just look that way. Here's what we have. Okay, the one that we did in the earlier example says that, see right here, this on this row, see you have the summation of 1 over n minus 1 over n plus 1. If you write it out, what does it become? It becomes 1 plus a half, and then the first, plus 1/2 minus 1/3, and then 1/3 minus 1/4. So as you can see, the middle terms, as you keep adding in the partial sum, the middle terms cancel themselves out. There's a plus 1/2, then there's always a minus 1/2, because everything increases by 1. So then so eventually everything's disappeared, so that your partial sum is actually end up being the first term subtracting by the last. See, as an example, as your book shows. See, S3, for example, end up being the first item, which is 1, minus the very last item, which is 1/4. And then the sequence continues that way forever. And you can then prove very easily. You can prove that S of k in general is just 1 minus k plus 1 on the next page. Now, if that is the case, see, sk end up being 1 minus 1 over k plus 1, and therefore, as k goes to infinity, S of k will converge to 1, and that is the answer to that solution. Now, in general, the telescoping series is something that is the series built in such a way that part of it, one item, is always getting subtracted by the next item, such that you end up being S of k, the final sum, the partial sum, always end up being the B1, always subtracted by the last term, the BK plus 1. So then the answer then becomes very, very easy most of the time. So as an example here, a quick simple example, example 5.12, please do that as part of your homework. So we have come to the end of this section. So for homework, on page 466, please do problems 69, 75, 79, 81, 82, 85, 87, 88, 89, 93, 95, 97, 99, 101, 103, 105, 107, 109. And when you're done with the homework, please do the student project, okay? Right before the homework, where you're supposed to calculate Euler's constant. And it makes a very interesting problem. However, it does have the book is negligent in this problem in giving hints, okay? So I wrote down extra hints in your homework description, that you have to consider the definite integral from k to k plus 1 of 1 over x as area under the curve. In other words, I would like you to think about this. K plus 1, 1 over x dx. And is what I mean. I can't type that in the description because YouTube doesn't allow certain symbols, not even the larger than or smaller than. I don't know why, but that's how they are. So you need to consider this, bear this thing in mind in order to solve this problem. And then and another one is, in other words, you need to consider the area under the curve. Sorry, I knocked something off. Okay, you need to consider the area under the curve of this integral. And also, similarly, you need to consider the same integral, except that you need to go consider from 1 to k of this thing. And yeah, these two integrals will help you calculate Euler's constant. Well, they should have mentioned it. The book should have mentioned it, but I don't know why they didn't. Not important. It still makes, once you realize that, then it makes for a suitably challenging but still doable project. That is actually very nice, okay, what it says. So I'll let you read it and discover how awesome Euler's constant is. And I should of course mention that Euler is the greatest mathematician of all time. So please go do your homework, and when you get back, I want to talk about it, and especially how to do Euler's constant. Okay, now you are done with your homework. Let's talk about it. Now first, let's look at problem 79. That is, we just have to prove something like it converges or diverges or something like that. So the proof is for 79 is quite straightforward. I didn't do the sum of sequence like your book wants, because that sounds like a lot of work. We'll just do it very simply. Look at from this side. It's for n bigger than or equal to 2. So if n is bigger than or equal to 2, you add an n to each side of the inequality, and then you divide by n plus 2. You will end up with n over n plus 2 is bigger than 2 over 4. Okay, and so each n over n plus 2 is bigger than 2 over 4, which is 1/2. So then the sum is bigger than sum of 1/2 from 1 to infinity. So you have an infinite number of 1/2s added up. Well, that of course goes to infinity and it diverges. And that's 79. 81 is a telescopic series. If you break up the fraction, you can do it by hand or use the calculator. Either way, but it's a pretty easy fraction to break. So once you notice it's telescopic, so s of k, the partial sum, is equal to the first number, where n start at 1. So the first number is 1 over 1 plus 1. And the last number is 1 over is it k plus 1 or k plus 2? Probably k plus 2, but what do we care? The point is, it goes, as k goes to infinity, this thing converges to 1/2, and that's correct. And then next, we have problem number 82, which is the sum of something. That again, we can use a quick trick to solve this one. 82, you have sum of 1 over 2n plus 1. So then, which is bigger than, I make the denominator a little bigger, so the whole thing is bigger than 1 over 2n plus 2, the sum of, right? And then you factor the 2 out, because you're allowed to do that, factor out constants. It becomes sum of 1 over n plus 1. Well, sum of 1 over n plus 1 is just the same as sum of 1 over n with the index adjusted. That is, you start counting n at 2 instead of at 1. So that will work out. And that, of course, diverges because that's the harmonic series. And that's the end of problem 82. Next, let's look at problem 91. We have a series that doesn't quite look like a geometric series. However, if you rearrange the terms, then you realize it is. So once you write it out, it ends up being pi to the power n over e to the power 2n. Okay, the power on top is double the one as the power on bottom is double the one on top, and then you can rewrite that as the pi over e squared to the power n. Once you realize that, then r is the stuff inside pi over e squared, and being that e is bigger than 2, pi over e, and pi is 3 point something, e squared is bigger than 4, so 3 point something over something bigger than 4 is less than 1. Therefore, the r is less than 1, and therefore the series converges. And that's the end of that. Now next, let's look at problem 97. Problem 97 wants you to write a simple little fraction into some kind of infinite sum. And the reason that works is because of the geometric series formula. The geometric series says that the infinite sum of certain things under certain conditions can be written as a simple fraction, such as this one. Okay, this is the example the book gave. If you have the sum of yn, of course y has to be less than 1, the absolute value has to, then this equation holds. So then, but now we're going to work backwards. We're going to take a simple looking equation and write it into an infinite sum. And so how do we do this one? Well, we will factor out the x and write down the bottom as 1 minus, and of course then you have to stick a negative sign in front of x, and then fill it into the formula, and then put the x back in. See, x, we factor out 1x, we put it back in so everything looks decent, and that's your answer. How to make a simple fraction into a big, long series. And next, 99, okay. the same thing. We're still trying to turn a simple fraction into a big long series. You follow the equation. You turn sine squared x into a -1, so that it becomes subtraction, and then plug it all in, and it comes out. And the -1, so you might have to take the -1 out. That's just a habit, I guess. All right. And the next problem, 101, we have a telescopic series. For telescopic series, you always end up being S of k, the partial sum, equals the first item minus the very last one, because that's the only one that survived. Everything else got added and subtracted until it's all gone. So the partial sum in this case equal to 2 minus 2 to the power 1 over k plus 1. So as k goes to infinity, that fraction goes to 0, and 2 to the power 0 is 1. So 2 minus 1 is 1. And that is where the series goes. Okay, now problem 103, the same thing. By the time you get done, you realize that it's a telescopic series. So your S of k is just the first thing minus the very last item, which is, in this case, it happens to go to infinity because it's just the square root of k. To be exact, it goes to negative infinity, but that's good enough. The point is, it diverges. The last few problems follow the same telescopic pattern. 105 is telescopic, so you take the first term minus the last term. That's actually the answer. We don't even have to figure out what that is. 107, the same thing. The first, I think you might have to, 107 has a slight catch, is you have to break up that function to show that it's telescopic. Now that is, break up the fraction, see right here, this thing breaks up into this one. This looks different than what we normally do for breaking up fractions, but the principle is the same. In that if you try to put this thing under the common denominator, you will quickly come up with this. See, that's why it works. And then, if it's telescopic, then the first term minus the last term, and that is your answer, being that the last term has gone to 0. And then finally, problem 109 is slightly longer, but the same principle. Okay, if you write it out, then you realize that it's, again, a telescopic series. So then the first term, the middle terms all kind of wipe each other out. So you only have the first term and the last term left. And the last term happens to go to 0 because it's given that way. Fn goes to 0 as n goes to infinity. So this thing goes to 0, which means you just have f1 left. And that's the answer. And that's the end of this section. But before we finish the section, we need to do Euler's constant. Now this is on page 465. Euler's constant is defined as the difference between the harmonic series as you add it up, and minus the natural log of that of the k. As it turns out, as you add up the harmonic series, the difference between the harmonic series and natural log approaches a fixed number we call gamma. Why do we call it gamma? I have no idea. You think that it'd be better if we just call it A or something because it's just a number. But gamma sounds so much more profound and intellectual and clever, right? So we're going to call it gamma, actually. Yeah. So, and math, a lot of times like to use Greek letters because it looks fancier. And we like fancy. So then, but remember, gamma is a number, okay? That's all it is. Now we are going to show that somehow the harmonic series is somehow related to the natural log, which is very interesting fact that's discovered by Euler, of course, who is the greatest mathematician of all time. So first we are going to show that the tk is a monotone decreasing function. To do that, of course, we have to show that. And to show monotone decreasing, we have to show that the next term, which is tk plus 1, has to be less than tk. All right. Now, to show that, what we're going to do is, well, first we figure out what it is, right? What is tk? Tk, let's write it out. Tk plus 1 is, following that formula, is 1 plus 1/2 and then all the way add up to 1 over k, and then up to 1 over k plus 1. All right, and then minus the natural log of k plus 1, being that we're doing tk plus 1, right? And then tk then is most of that stuff is 1 plus 1/2 all the way plus 1 over k, but we don't have that, and then minus natural log of k. Okay, so then what we're going to do is calculate what is tk plus 1 minus tk. So to prove that, here's what we're trying to prove, okay? To prove this thing, or which means that tk plus 1 minus tk has to be less than 0, is what we're trying to prove. So we don't know this yet, but this is what we're driving for. And now we've gone so far, and then we do tk plus 1 minus tk to see if it's less than 0. So tk plus 1 minus tk equal to that stuff minus this. So this pile of stuff is all taken out when we're doing the subtraction. We will have this thing left, 1 over k plus 1 minus the natural log of k plus 1. And this one will be subtracted out, becomes plus, okay, natural log of k. So that is the subtraction. But that, and this thing has to be less than 0, but it doesn't look that way. How do we know this thing is less than 0 or not? And here's the, so here comes the first trick. What we're gonna do is look at this integral, okay? Now the integral, as I mentioned in the hint, we need to integrate k to k plus 1 of 1 over x dx. And why do we need to integrate that? Because we have to consider the area under the curve. Okay, we know what 1 over x looks like. It looks like this. Okay, and then here is, let's say here is k, we're integrating, right? And here is k plus 1. And it goes, now this integral from k to k plus 1 is bigger than 1. This distance is just 1, right? This is 1, okay? Now the area of this area is under the curve, is everything down here, is bigger than the area of this rectangle, which is 1 times k plus 1. This, because this height is k plus 1. Sorry, I said that wrong. This is bigger, this height is actually, let me figure out what I'm talking about. Is less than 1, the height here is 1 over k plus 1, because this is 1 over x, right? The function is 1 over x, so the height is 1 over k plus 1. All right, so the area under the curve of this whole area here is bigger than this rectangle, which has 1 times 1 over k plus 1 as the area. So here's the area of just the rectangle, right? So and the area on the curve is somewhat bigger. So that is actually the trick. Now, and how does that work? Because we also know what this integral is. The integral stands for 1 over x is, of course, the natural log. So this integral end up being the natural log of the top bound, k plus 1, okay, minus the natural log of k. Now this is the integral, right? The subtraction for the definite integral, which is going to be bigger than 1 over k plus 1. Now, did I say k plus 1 or k? Yeah, k plus 1. See, right there. Now, as you can see where this is going. So once we have established this inequality, we'll rewrite it as, move everything to this side of the inequality. It becomes 0 is bigger than 1 over k plus 1. Move everything over so it becomes negative. I mean, change the sign. Minus natural log of k plus 1 plus natural log of k. And what is that? That is exactly this thing. See, term for term. That is so this is the same as tk plus 1 minus tk. And so therefore, the TK's partial sum is monotone decreasing because each k plus 1 is less than the TK before. So we have proven this fact. Okay, so we are done with part 1. Now that we have proven the TK series is monotone decreasing, we're going to prove part B that it is bounded below by 0. If we can do that, then by the monotone convergence theorem, it converges. So how do we prove this thing is bounded by 0? In other words, each TK has to be bigger than or equal to 0. So to prove that, let's write down what is TK anyway. Now, so part B, we need to prove TK is bounded by 0 on the bottom. Now, so we'll rewrite TK. Actually, we're not going to rewrite it. That's just what it says over there. TK is that thing. Should we write it again? Yeah, why not? So TK equal, I'll copy it again right here because we're doing it again. Sometimes it's good to rewrite the problem because it solidifies in your mind and so that you can see it better. Minus natural log of k. All right. So that is the problem, and the way we're gonna do pull this trick, is by doing another integral. Okay, that area under the curve, and here's the integral we're gonna consider. Again, is 1 over x, but this time we're gonna integrate from 1. Here's 1 to k, or something. Yeah, 1 to k. Here's k. And we're going to integrate, so then we have a bunch of stuff, okay? And then the Riemann sum, what we're going to do is prove that this thing is, we're going to prove, and let me look at it. So what we're going to do is that we're going to do the Riemann sum, but the division is not small, it's just by 1. So we have 1, and draw the rectangle here, that's 2. And draw another rectangle and so on all the way to k. Okay, yeah, all the way to k. Here's k. Anyway, so then the integral, then the Riemann sum all the way to k is going to be bigger than the 1 over k because the way is the left-handed sum, right? So each one is bigger. So then the argument then becomes the sum of 1 to k of 1 over n, the area of each triangle, okay, is starting at 1 and all the way up to k is going to be bigger than k. There's the last one, k. Is going to be bigger than the area under the curve from 1 to k of 1 over x dx. Because yeah, each one is going to be bigger, and we come all the way the area to the end. So we have a lot more stuff in from 1 to k of the harmonic series than say the area under the curve. Does that look right to you? All the ends are taken care of. So we're doing the left-hand Riemann sum for all this, except that this is not narrow. This is all unit of 1, and we go all the way up to k. That looks right to me. All right. So now, therefore, this is strictly bigger. And if that's the case, now what is this thing? This thing is, of course, natural log of k minus natural log of 1 when you do the integration. And natural log of 1 is just 0. So it equals the natural log of k. And therefore, this sum is bigger than natural log of k, and therefore tk is bigger than 0. So that's the second argument, is that tk is bounded by 0. So now that we finished a and b, we basically have it made, which means that the sequence converges. It converges to some number, and we will call it gamma. Okay, and so the next part is we need to figure out what gamma is. Next, let's do part 3a. The next step is we have to prove something like 3a says we have to do something similar to this. Okay, we have to prove that natural log of k plus 1 minus natural log of k is smaller than 1 over k, so we'll prove it similarly to this. So we are trying to show the natural log of k plus 1 minus natural log of k. So we'll draw the integration graph again, okay? And here, that's natural log of k plus 1 and natural log of k. Here's k, and here's k plus 1. That is just, this is the area under the curve of the integral. Now, however, this will be, is a smaller, but that will be smaller than if you draw the rectangle from k, right? So the area under the curve, which is that this thing equals to, let's see, I'll write it right here. This thing equals to the integral of 1 over x dx, as before, okay, but I'll rewrite it here from k to k plus 1. This thing is going to be less than the k rectangle from the left side. So if this distance is 1, so the area is 1 over k. So the height here is 1 over k, 1 over k, 1 over k times 1. See, length times width. So that inequality holds in a similar way. Therefore, if we have tk minus tk plus 1, which is, we have done something similar here. This is tk plus 1 minus tk is this thing, right? So the other way is natural log of k minus natural log k plus 1 is equal to, well, I'll just write it down. So tk minus tk plus 1, sorry, what? Yeah, tk minus tk plus 1 equal to, I have to write it all down. There is no way around it. Equal to the negative of this thing right here. I will write it this way, okay? So it will be equal to, let's see, where is it? That becomes positive, equal to natural log of k plus 1 minus natural log of k, that becomes negative, and then minus 1 over k plus 1. I'm running out of space here, which is, but I will finish this part, okay? Being that it equals to this, we already said that this thing, okay, is less than 1 over k, right? So this part right here is less than 1 over k. So that this is less than, I'll write over here, this is less than 1 over k minus 1 over k plus 1. If we write it, yeah, this subtraction out. See? Okay, so that, I think that's it. That's what we're supposed to do for CA. 3a, which says that we have to prove this thing is less than 1 over k. So then, let's see, am I done? Let me check. Actually, that's part 3b that we just finished. So we have, so next, let's go to 3c, and I better wipe the board. I got no space left. Now we're near the end now, so next let's do 3c, where we have to turn this thing into a telescoping sum, which is quite ingenious actually. So part 3c, let's consider tk equal tk minus tj. J is some other number, okay? What number is that? We don't care right now. Okay, and we're just going to pull another trick. So the trick is we are going to write this thing in terms of telescopic sum where j is bigger than k. Okay, some bigger number. All right, so that would, and we will write it just like the telescopic plan, which is we'll have tk. Okay, first we'll subtract tk plus 1, and then we'll add it back out, tk plus 2, and then, sorry, tk plus 1. Okay, we're adding the same thing. That way we're not changing anything. And then minus tk plus 2, and then plus tk plus 2. And we keep doing that until we get to tj minus 1. So then we'll let's see, we'll do minus all the way up to tj minus 1. Okay, then we add tj minus tj plus 1, and then finally we'll get to the minus tj. So being that is I'm getting my t and j confused. This is a t, and the other thing is a j. So finally we get to tj. So this is being a telescopic series. Nothing's different. This is the same as that one, right? We just added and subtracted and wasted our time. But we did that for a specific cause, I guess. And the point is, so that equals to, what is that? No, sorry, that is less than. We're going for this thing, okay? Tk minus tk plus 1 is less than each one of those things, okay? It's less than this thing down here, k 1 over k minus 1 over k plus 1. So we're gonna, that's what we're shooting for. So this is less than 1 over k, starting at the first one, 1 over k and minus 1 over k plus 1. And then that's the first group, okay? And then the second group is plus 1 over k plus 1. And then minus 1 over k plus 2. See, you see how clever this is. And you continue to go, where are we ending? So eventually we'll end up with, let me think about this. Sorry, this is j minus 1. I wrote that wrong. There. It should be, yeah, j minus 1. And then eventually get to j. Now, so this one, following the same pattern, then eventually it will get to 1 over j minus 1. Sorry. 1 over k. Yeah, actually, I'm right. Why did I erase that? Okay, that is what I have. Eventually, you get to 1 over j minus 1 minus 1 over j. Okay, that's the last term. So that once you keep track of all this stuff and make sure everything come out correct, then we have the telescopic sum then get shrunk down into 1 over k minus 1 over j. And that is what we are shooting for in part 3c. Next, let's look at 3d. 3d says, being that this is true, let's allow j to go to infinity. What happens when j goes to infinity? Remember, tk approaches gamma. Okay, so when j goes to infinity, then tk minus tj. Maybe I should write it down. Yeah, let's write it down. So limit of tk minus tj, that's a t here, not a j, t. Limit of tk minus tj as j approach infinity is equal to the limit of of tk, let's see, limit, that is just tk, because tk is not going anywhere, because we are only allowing j to go to infinity, so tk stays. Okay, so tk doesn't change. As j goes to infinity, this goes to gamma, and that is going to be less than 1 over k, because k doesn't change. And then j goes to infinity, that becomes 0. So tk minus gamma is less than 1 over k for all k's, and which means that as k gets bigger, you can approximate gamma by figuring out what tk is, calculate the partial sum. What is tk? Well, tk is, so for example, your book wants you to calculate it within, what did they say? 0.0001, that is within 1,000th, right? So we're going to do that. We have T1000, which is the gamma then equals to, we can plug it in, we'll calculate tk, what tk is at when k is 1,000. To do that, you can either type sum into Desmos, okay, which is what I did. I didn't take a picture of it, but you get the idea. You just gamma is approximately at the 1,000th accuracy is 1 to 1,000. Type it into the decimal calculator by typing in the word sum, S-U-M. And once you type in sum, they'll let you enter the 1 and the 1,000 and 1 over n, which, yeah, it allows you to type in 1 over n and then subtract natural log of 1,000. That comes up with some number. See, like that. And that is the accurate calculation of gamma, the Euler's constant. And I also plotted the graph of this thing to show you. Where's my graph? Here it is. Okay, now take a look at the graph. See, should I make it bigger? Nah, that's big enough, maybe. Okay, let's see if you can see it clearly. Is this too bright? That looks okay. See, the dots are the sum of the partial sum of the harmonic series, and then the red line is the natural log that's adjusted upwards by about 5.8, because I was trying to eyeball it. See, I added 5.8 to it to see if it lines up, and before that it was the lines are far lower, different by about 5.7. So I decided the gamma was about 5.8, but as it turns out I was wrong, because eyeballing is not quite accurate enough. So, and the actual answer is actually 5.77. So, but as what you can see here is my eyeballing the result. And so please feel free to type the summation into plot the summation. Plot the series in, well, at least plot, this is the partial sum. Yeah, plotting a series. Well, the only thing you're going to be plotting is the partial sum, of course. And yeah, see, if you feel like plotting the partial sum, I have the link for plotting a series in Desmos under here. Yep, I do. So that looks very, very neat. Now, why do we care about Euler's constant? I have no idea. But the point is, Euler was able to, I don't know, figure all this stuff out. See, and that the harmonic series is actually very similar. It has many ways similar to the natural log. It grows there's one approach the other, as infinity holds, as they head for infinity, which is a very cool fact. Okay, and I hope you enjoyed it.